When it comes to the solar system, most of us imagine planets orbiting the sun on the same plane, like perfect circles in a textbook. But is the truth really that simple? Is it all just a strange coincidence? Or is there a deeper cosmic mystery waiting to be unraveled? In today's video, we'll dissect the biggest misconceptions about our solar system, and I believe you'll be surprised by what scientists have discovered. So don't look away. Make sure to watch until the end of the video so you don't miss any details. And if you find this topic fascinating, don't forget to hit subscribe and the notification bell to continue our journey of exploring the universe together. If we want to understand why the entire solar system has the astonishing order it does today, with planets, moons, rings, and even asteroids all orbiting according to almost unified rules, we need to go back billions of years when everything was still chaos. Imagine the universe at that time. No brilliant planets, no regular orbits, only a massive cloud of dust and hydrogen and helium gas drifting in the cold void. This cloud, which scientists call a protostellar nebula, was the raw material that would later form the sun and the entire solar system. At first glance, one might think that this formation was simply a matter of matter being pulled together by gravity, but the reality is far more complex. In space, each dust grain or gas molecule has its own tiny gravitational pull. Normally, these forces are not strong enough to overcome the internal pressure pushing outward from the gas and dust, so everything just floats in balance, until one day a kick from the universe, possibly a shockwave from a nearby supernova explosion, broke that fragile balance. Gas and dust began to contract, particles collided constantly and stuck together, gradually forming small clumps of greater mass. Over time, these clumps of matter merged into larger bodies, and their increasing mass created stronger gravity, pulling in even more surrounding material. The result was that, at the center of the nebula, one region became especially dense and hot. That was the protostar, or our infant sun. Although nuclear fusion had not yet ignited in its core, the protostar was already the nucleus of the entire forming system. But the formation was by no means neat. Material from the original nebula rained down onto the protostar from all directions, creating a chaotic scene like millions of small rivers all flowing into one ocean. In the process, particles collided again and again, and each collision canceled out some of their angular momentum. Gradually, from the initial chaos, a rule emerged. Only one common direction of motion remained, which most particles followed. This is the deeper reason why all the planets today orbit the sun in the same direction. To make this easier to visualize, physicists often compare it with a simple experiment. Stretch out an elastic sheet, place a heavy ball in the middle, then roll smaller balls around it. Some balls will collide and stop, but the remaining ones will begin moving around the center in a stable direction. Of course, the universe has no friction like the sheet, and this event happened in three-dimensional space instead of a two-dimensional plane. But the general principle is the same. From chaos emerges order. As the protostar continued to pull in material, the rest did not fall straight into the core, but began to accumulate into a protoplanetary disk around it. In that massive disk, dust and gas kept clumping and merging into larger and larger bodies. Some small clumps soon collided and shattered, but others were lucky and resilient enough to keep growing, becoming planetary embryos. From these planetary embryos, the planets we know today were gradually born. Interestingly, this process did not only happen at the scale of a star system. When giant planets like Jupiter or Saturn formed, they too had small disks of material surrounding them, just as the Sun once did. And from these small disks, their moons were born. That is why the regular moons of the giant planets also orbit in the same direction as their parent planet and lie on almost the same plane. Looking at Saturn's ring system, where billions of ice and rock particles move rhythmically like a clockwork machine, we can glimpse a faint picture of the solar system when it was newly formed. Of course, not everything is perfect. Planetary orbits have slight tilts of a few degrees, and many irregular moons, often captured from outside, orbit backwards or on skewed paths. But overall, order dominates. This reflects an important law of nature. From the initial chaos, through countless collisions and interactions, a stable structure eventually emerges. Scientists call this phenomenon emergence through self-organization. Just as a storm forms from turbulent air currents in the atmosphere, our solar system is the result of self organization from primordial chaos. What makes this story even more fascinating is that it not only explains the solar system, but also opens the door for us to understand thousands of other star systems in the Milky Way. If this self organizing process is a universal law, then perhaps somewhere out there, other planets are also orbiting regularly around their stars on unified orbital planes. And who knows, on one of those planets, life may also be self organizing in its own way. When we look out into space, there's an important distinction to make. The boundary of interstellar space and the true boundary of the solar system are not the same. The Voyager mission, with the two spacecraft Voyager 1 and Voyager 2, gave humanity a unique opportunity to touch interstellar space. When these probes cross the layer called the heliopause, where the solar wind weakens and is overwhelmed by the interstellar wind, it was a historic milestone. Many people quickly assumed that meant Voyager had left the solar system. But in reality, the boundary of a star system is not defined by winds, but by gravity. To understand this, we need the concept of the Hill sphere. This is the region of space in which the gravity of a body is strong enough to dominate the orbits of smaller bodies. A classic example, the moon orbits the Earth because it lies within Earth's Hill sphere, meaning Earth's gravity at that distance is stronger than the sun's. Similarly, the sun has its own enormous Hill sphere, encompassing all the planets, asteroids, and even icy bodies in the farthest reaches. Only when an object escapes beyond this region does it truly leave the solar system. Interestingly, the sun's Hill sphere is not a perfect sphere. The reason is simple. The stars around us are unevenly distributed, and each has its own gravity affecting space. Take, for example, the Alpha Centauri system, about 4 light years away. This is not just one star, but a binary system with a total mass greater than the sun's. The pull of Alpha Centauri compresses the sun's Hill sphere on that side. Conversely, toward Barnard's star, a small red dwarf about 6 light years away, the weaker pull allows the sun's influence to extend farther. Thus, the boundary of the solar system is not a sphere, but a distorted shape, stretched toward the weak side and squeezed on the strong side. When an object moves near the edge of this Hill sphere, its orbit becomes extremely fragile. Just a small nudge from a passing star, from the faint but constant pull of the interstellar environment, or even from a collision with another body, can be enough to eject it from the solar system. That is why astronomers believe that objects belonging to the sun in a stable way only exist out to about 1 light year, even though in theory the sun's Hill sphere could extend up to 3 light years. Beyond the region of the known planets and even the Kuiper belt, we enter a legendary area that modern science calls the Oort cloud. This is a massive spherical shell surrounding the solar system, containing billions, perhaps trillions of small icy bodies. Although we cannot yet observe it directly, much indirect evidence suggests that long-period comets, those with orbits lasting tens of thousands or even hundreds of thousands of years, originate from this region. In a sense, the Oort cloud is the final fence marking the presence of the solar system in the cosmic sea. To grasp its immense scale, imagine this. Voyager 1, the spacecraft that left Earth in 1977 and is traveling at more than 60,000 kilometers per hour, will need at least another 300 years just to reach the inner edge of the Oort cloud. And to cross the entire region, a number that overwhelms anyone, from 30,000 to 150,000 years. In other words, even if we launched spacecraft tens of times faster than Voyager, traversing this outer layer would still be nearly impossible with current technology. From these colossal numbers, we realize one thing. The solar system does not end with 9 or 10 planets, as textbooks often say, but is a structure stretching so far that it surpasses ordinary imagination. And what's fascinating is that this boundary is not static. As the Sun and the entire planetary system orbit the center of the Milky Way at more than 800,000 kilometers per hour, the solar system constantly changes position, passing through denser or sparser regions of the interstellar medium. These changes can distort, shrink, or even expand the Sun's gravitational boundary over time. Now let's broaden our view a bit. If the Sun can dominate a region spanning up to several light years, How vast would the sphere of influence of a star hundreds of times more massive than the Sun be? In theory, an extremely massive star, isolated in space and not disturbed by neighbors, could control bodies within hundreds or even thousands of light years, comparable to the size of a small galaxy. In extreme cases, such a stellar system might extend so far that the concepts of star system and galaxy blur together. However, in reality, most massive stars form in dense star clusters. There, the gravity of dozens or hundreds of other stars constantly competes, severely limiting the domain of each star. Even the Sun is not alone. It is part of the Milky Way, where hundreds of billions of other stars together dance around the galactic center. This makes determining how large the solar system truly is not just a scientific question, but also a philosophical one. What is certain is the true boundary of the solar system is not a fixed number, but a flexible concept depending on how we define it, by the solar wind, by gravity, or by the orbits of the most distant bodies. But under any definition, one common point emerges. The solar system is far vaster than popular imagination, and within that vastness, we are merely a tiny speck of dust orbiting a modest star. When leaving Earth's orbit, we continue our journey to the fiery red neighbor, Mars. In this miniature model, Mars is only a few dozen centimeters farther from the Sun, but for humanity, it represents a journey full of aspiration. Numbers that seem dry, like the average distance of 225 million kilometers, suddenly become vivid when you imagine. If the Sun were a large ball placed here, then Mars would be just a tiny speck of dust lying out of arm's reach. It is precisely this distance that makes the dream of sending humans to the red planet both difficult and fascinating. Leaving Mars, we encounter the asteroid belt, a chaotic land filled with millions of small celestial bodies. In our model, it may be only a few dozen centimeters from Mars, but in reality, this region stretches across hundreds of millions of kilometers. Many people mistakenly believe that this is a crowded region, so dense that spacecraft would struggle to pass through without collisions. In fact, most of the space there is empty, with asteroids separated by hundreds of thousands of kilometers. Yet these fragments are living fossils of the solar system, helping us better understand how planets were formed. A little farther on, we reach Jupiter, the giant of gas. If the Sun is the center of the model, then Jupiter is like the first colossal milestone as we step farther out. At the miniature scale, it may be only about half a meter away, but scientifically, this distance represents a major boundary. Inside are the small rocky planets, outside are the gas giants. Jupiter impresses not only with its size, more than 300 times the mass of Earth, but also with its role as a cosmic shield. With its enormous gravity, it attracts or deflects many dangerous celestial bodies, perhaps helping protect Earth from catastrophic impacts over billions of years. A little farther still, we come to Saturn, the pearl of the solar system. Its famous rings have long enchanted humanity, making everyone long to see them firsthand. In our model, the distance from the Sun to Saturn is just over 1 meter, but in reality, it is so far that light takes more than an hour to travel from the Sun to it. When you imagine this time span, remember that the radio signals NASA sent to the Cassini spacecraft also had to wait over an hour to arrive. This shows how every step outward in the universe is a challenge beyond imagination. Continuing outward into the distant regions, we reach Uranus and Neptune, the two icy giants. They are not only distant in space, but also mysterious in nature. Uranus, with its axis tilted almost flat along its orbital plane, is a fascinating exception that science has yet to fully explain. Neptune, on the other hand, is famous for its violent storms, with winds blowing faster than the speed of sound, the fastest in the solar system. In the miniature model, they are just a few meters away from the Sun, but in the universe, the distance amounts to billions of kilometers, so far that Voyager 2 took more than a decade to reach them. And then, out there, lies Pluto, the dwarf planet that stirred so much debate. In the model, it lies more than 4 meters away, a small distance in a room, but in reality, it is a dark and frigid place where sunlight is as faint as a full moon on Earth. Pluto's demotion from planet to dwarf planet in 2006 sparked much controversy, but it also broadened our perspective on celestial bodies in the solar system. However, the story doesn't end there. If you go farther still, you will encounter the Kuiper Belt, home to countless icy bodies, including many other dwarf planets yet to be discovered. This is also the birthplace of short period comets, visitors that pass by and return after a few decades or centuries. Farther still, you may have heard of the Oort cloud, a region surrounding the solar system at such immense distances that Voyager 1, despite leaving Earth in 1977, will take tens of thousands of years to pass through it. At this point, a natural question arises. So what about the nearest star? Alpha Centauri. In this model, if the Sun were just a tiny grain of sand, Alpha Centauri would be tens of kilometers away. Imagine we have traveled from one end of the room out to the street, and from there farther still to the other side of the city, and all this just to reach the nearest star. This vastness leaves us in awe. The solar system is immense, yet it is still just a tiny speck of dust in the cosmic ocean. After passing beyond Neptune's orbit, we officially enter one of the most mysterious regions of the solar system, the Kuiper Belt. If the asteroid belt between Mars and Jupiter is the gateway dividing rocky planets and gas giants, then the Kuiper Belt is considered the true boundary of the inner solar system. This is the home of countless icy bodies, primordial remnants left over from the formation of the solar system more than 4.5 billion years ago. In a scaled-down model, the Kuiper Belt might stretch from just a few hundred meters to a few kilometers from the position of our Sun. But in reality, it begins at about 30 astronomical units AU, that is, 30 times farther from the Sun than Earth, and extends out to 50 AU. This means that sunlight, which takes only 8 minutes to reach Earth, needs more than 4 hours to travel to the outer edge of this belt. That number alone is enough to make us feel the almost boundless immensity of the universe. In this distant land, the most prominent is Pluto. Once considered the ninth planet of the solar system, it was downgraded to a dwarf planet in 2006 by the International Astronomical Union. But that has not diminished its allure. With its icy surface, thin atmosphere, and orbital period of 248 Earth years, Pluto is still regarded as one of the most fascinating celestial bodies ever explored. In 2015, NASA's New Horizons spacecraft flew past and sent back the first close-up images of this dwarf planet, a world filled with nitrogen ice mountains and vast plains, appearing both alien and familiar. But Pluto is just a small piece of a much larger picture. The Kuiper Belt also contains other names, lesser known yet equally intriguing, such as Haumea, a body with an unusually elongated oval shape, rotating on its axis in less than 4 hours, or Makemake, a bright dwarf planet discovered in 2005. These objects, along with thousands of other small bodies, form a colossal cosmic archive that we have only just begun to scratch the surface of. Farther out, it is believed that beyond the Kuiper Belt lies an even more mysterious region, the Oort cloud. This is a hypothetical spherical shell surrounding the solar system at distances ranging from several thousand to tens of thousands of AU. If the Kuiper Belt can be imagined as a ring around the Sun, then the Oort cloud resembles a vast atmosphere enveloping the entire system. It is thought to contain trillions of icy bodies and to be the origin of long-period comets, wandering visitors that take thousands or even millions of years to return near the Sun. To help you picture it, if the Sun were as small as a grain of sand, the boundary of the Oort cloud could lie tens of kilometers away in the model. And the astonishing fact is that, to this day, no human spacecraft has traveled far enough to reach this boundary. Voyager 1, the most distant spacecraft, has only just touched interstellar space, but it will still need tens of thousands of years to cross the Oort cloud. This shows that what we know about the edges of the solar system is, in fact, just faint sketches. So why are these remote regions so important? The answer lies in the fact that they are the universe's time machines. The celestial bodies in the Kuiper Belt and the Oort cloud have largely never been significantly altered by the Sun or the giant planets. They preserve the chemical composition and matter almost in their original state from the dawn of the solar system. Studying them is therefore like opening a cosmic diary sealed for billions of years. But beyond scientific value, they also offer us a humbling perspective. When we imagine that out there, just on the fringes of the solar system, there may exist trillions of celestial bodies, Earth, our home, suddenly seems incredibly small. And though small, it is so special that it has created life, intelligence, and beings capable of sitting here reflecting on the very universe to which they belong. Ending the journey through the Kuiper Belt, we not only travel farther in space, but also delve deeper into our awareness. Each step forward is a reminder that the universe is not only vast, but also filled with countless wonders waiting to be discovered. And the mysteries at those distant frontiers may very well be the key to helping us better understand the origin, future, and meaning of humanity's existence. When mentioning the solar system, many of us probably think we already know quite a lot, from the positions of the planets, their familiar names, to a few outstanding features. But the truth is, the universe always holds countless surprises, and the deeper we explore, the more we realize that many concepts we believed since childhood are actually just popular science myths. That is precisely why today we continue our journey to dissect the most common misconceptions about the solar system, things that seem obvious but actually not quite so. One of the classic misconceptions is that many people believe the sun is a giant burning ball of fire. That image sounds reasonable because when we look at the sky, the blinding light and immense heat indeed make us think of flames. But if we call it fire in the ordinary sense, that is completely incorrect. Fire, as we know it on Earth, is just a chemical reaction when matter combines with oxygen. The sun is different. Its energy comes from nuclear fusion, a process in which hydrogen nuclei combine to form helium, releasing immense energy. Put simply, the sun is more like a natural nuclear fusion reactor than a giant bonfire, and it is precisely thanks to this mechanism that it can sustain light and heat steadily for billions of years, instead of burning out quickly like an ordinary flame. Going a bit further, let's come to Pluto, the celestial body once considered the ninth planet of the solar system. Many people still think that Pluto is the final point, the farthest boundary of our system, but the truth is different. Beyond Pluto, the universe holds an entire icy wilderness known as the Kuiper Belt. This region contains countless small bodies of ice and rock, and it is here that truly marks the gateway to the outer reaches of the solar system. Not only Pluto, but also a host of other dwarf planets, such as Haumea, Makemake, or Eris, and even strange objects like Sedna, with an orbit stretching hundreds of astronomical units. In other words, calling Pluto the last is no different from standing on the shore and thinking the ocean is only as wide as the horizon we see. Another common misunderstanding is about planetary rings. Since childhood, most of us have been taught that Saturn is the only planet with rings, and the image of a planet with a flamboyant hat of rock and ice has been etched into memory. But in fact, Saturn is not alone. Jupiter, Uranus, and Neptune also have their own ring systems. They are fainter, harder to observe, but they do exist. For example, Jupiter's rings are composed mainly of dust produced by collisions of its moons. Uranus has 9 distinct bright rings and several faint ones, although the great distance makes them difficult to observe. So if someone ever told you that only Saturn has rings, you can now smile and explain that the solar system is always more diverse than what simplified textbooks convey. Speaking of comets, many people imagine that they always possess a long, glowing tail as they streak across the sky, but in reality, comets don't always look so impressive. When far from the sun, they are merely ordinary blocks of ice and rock with no tail. Only when they move into the inner solar system does the sun's heat cause the ice to vaporize, forming a cloud of gas and dust called the coma, along with the characteristic tail that always points away from the sun. Interestingly, sometimes a comet can have 2 tails, one made of dust and one of ions. This is what makes every comet's visit to Earth a rare visual feast. Next, let's talk about Mercury. Because it is closest to the sun, many assume it is the hottest planet, but the truth is the opposite. Venus is the hottest planet in the solar system. Why is that? Because Mercury barely has any thick atmosphere to retain heat. During the day, it scorches, but at night, it freezes. Meanwhile, Venus has an extremely dense atmosphere filled with CO2, creating an immense greenhouse effect that traps heat and keeps its surface temperature at an average of about 462 degrees Celsius, hotter than even the hottest temperatures on Mercury. It's fascinating to see that sometimes being closer to the sun does not mean being hotter. Another misconception that few pay attention to is about the mass distribution in the solar system. Many assume that the planets, with their massive appearances, make up a significant portion of the mass. But in reality, the Sun alone holds more than 99% of the total mass of the entire system. This means that the whole Earth, Jupiter, Saturn, and everything else you know only account for less than 1%. It is this dominance that makes the Sun the gravitational center, keeping all the planets in orbit. Without its immense mass, the solar system would never be as stable as it is now. And finally, one of the biggest misconceptions that the solar system formed at the same time as the Big Bang. In reality, the Big Bang, the event that created the universe, happened about 13.8 billion years ago. Meanwhile, our solar system only appeared about 4.5 billion years ago, making it nearly 10 billion years younger than the universe. It was born from the collapse of a massive cloud of gas and dust, where most of the matter concentrated to form the sun, while the rest coalesced into planets and asteroids. This shows that even though we regard the solar system as everything, it is still just a tiny fragment of the universe's grand design.